All right, so let's start the problem solving session. So today we are going to solve a problem from uniform circular motion and gravitation. Okay, all right. The first question is this one. Let's see. So here it asks us to calculate the centripetal acceleration. Okay, so what is the centripetal acceleration? So if you remember from the theory class, the definition of the centripetal acceleration is something like this: AR equal to V square over R. Okay, so this is the centripetal acceleration, and here you see that we are given the radius, and that is equal to 0.6 meter, and we are given the mass of the ball and something. So it says that the ball makes 2 revolutions in a second. Okay, so to calculate the centripetal acceleration, the first thing here we need to determine is what is the velocity, right? We already know R, the radius is 0.600 meter. Okay, so here you can see that. So what is V? Now, if you remember from the theory class, the V is this 2 pi R F, where F is the frequency. Okay, now what is frequency? So frequency, if you remember, frequency is the number of full turn in 1 second or full revolutions in 1 second. So here you see that this tells us that the number of revolution in 1 second. That means this 2 is equal to the frequency. So we are also given frequency equal to 2 rev per second. Okay, so now I think it's simple. We know radius, we know frequency, we can easily calculate the velocity. Okay, and then we can plug this value into the equation of centripetal acceleration. Okay, and calculate the centripetal acceleration. Okay, so this will be 7.54 meter per second square, and then so the centripetal acceleration I got is equal to 94.7 meter per second square. Okay, so easy. So here the velocity is not directly given. We have to determine velocity from this equation, 2 pi RF. Okay, all right. So let's move on to the next problem. Is very similar to the last problem. Again, here we are given the radius and time period. Okay, so in the last problem we are given the frequency. In this problem we are given the time period, right? So this is the radius and this is the time period. Okay, so to calculate the centripetal acceleration, we again need this equation, AR equal to V square over R. Now again, we are not given V directly, so we have to calculate V, but this time we are not given the frequency. Instead, we are given the time period. So instead of using the frequency, let's use the equation of velocity, which relate the radius and the time period. Okay, so 2 pi. Now R is 384,000 kilometer. right? And you know that kilometer is not a standard international unit. So what we have to do is we have to multiply it by 10 to the power 3 to convert it into meter. And also 27.3 days is not standard international unit. So day to hour, so 24 hour in one day, and in 1 hour we have 60 minutes, and in 1 minute we have 60 seconds, right? We have to find the time in second. Okay, so this is the time in second in the denominator. Okay, now if you plug these values correctly in your calculator, you will see that the velocity of the moon around our earth will be equal to this 1023 meter per second. Okay, so once we know that, the rest of the thing is very simple. You just plug this value, but make sure you plug in correct unit. Okay, okay, so again here you have to convert it into meter. Okay, so then plugging this value in your calculator, it should give you this value for the centripetal acceleration. So the centripetal acceleration of moon around our earth is 0.0027 meter per second square. All right. All right, so the next one is this one. All right, so we have a rotor of ultra centrifuge and that rotates at this RPM. Okay, so RPM is revolutions per minute. Okay, so revolution per second is the frequency. Okay, so this is basically frequency, but given in rev per minute, which is not useful. So we have to convert it into second, right? So minute to second, we have to convert it into minute to second. Okay, so rev per minute, and then 1 minute divide 60 seconds, right? So minute cancel out, so 50,000 divided by 60 rev per second. So this is the frequency in revolution per second in standard international unit. Okay, so again we have to calculate the centripetal acceleration. So first v will be 2 pi rf. 2 pi, I mean 2 pi is 2 pi, r is 6 centimeter. Okay, 6 centimeter means this meter to centimeter, so you have to convert centimeter into meter, so we need 10 to the power minus 2, and then frequency is 50,000, okay, rev per second. So this will give you, if you correctly plug these values into your calculator, it should give you this value. Okay, so once you have that, then calculating centripetal acceleration is easy, and it will be v square over r. V square is 314 meter per second square, and r is 6 centimeter. Okay, so make sure you again convert centimeter to meter. So the centripetal acceleration is, for this problem, is 1.64 times 10 to the power 6 meter per second square. Okay, so this is the centripetal acceleration. All right. So let's move on to the next problem. All right. All right, so we are given the mass. Okay. So this is the mass of the ball. We are given the radius. Okay. So from here to here, okay, the radius of the circle is 1.110 meter. And then it says that determine the minimum speed the ball must have at the top of its arc so that the ball continues moving in a circle. Okay, so we have a ball that is moving in a vertical circular path. Okay, so we have to calculate first the minimum speed when the object is position 1. So at this position we have to calculate the minimum speed of this ball. Okay, so the easy way to solve this problem is to draw a free body diagram, but for this problem it's already have here, so we don't need to do much. Okay, but we have to understand that when we have a ball and it is traveling in a vertical circular path, okay, what forces we have for this ball at position 1. Okay, so the ball should have the gravitational force mg, and gravity is always downward. Okay, and because the ball is connected with the hand by a string, we should have the tension force. Okay, let me use another color for tension force because both are downward. Okay, so this is the tension force. Okay, so basically we have tension force and we have the gravitational force mg. Okay, and because the circle is this one, okay, so the centripetal acceleration's direction is also this one, okay, toward the center of the path, the center of the circular path. Now if I write the Newton's second law, Fy equal to ma I can write that minus t minus mg, because both are downward, so we have minus sign for both, and centripetal acceleration is also downward, so another minus sign. Okay, but the good thing is all the minus signs can be cancelled. Okay, if you multiply all the terms by -1, you can write something like this: t plus mg equal to m v square over r, because ar, the centripetal acceleration, is equal to v square over r. Okay, now we have to calculate v, right? So let me solve it for v square first. So v square will be this equation. Okay, so v will be this equation, right? Now okay, so I mean ft or t, you know that is the same thing. So t or ft, whatever you use, is the tension. Okay, so here in this equation it use, I mean in this picture they use ft, but I use t. Remember that both represent the same thing. Now we have to calculate v minimum. Okay, so we can determine v minimum by knowing that v will be v minimum when t is minimum. Okay, when the tension is minimum. Okay, now because we do not have any information about tension, we can assume that tension is equal to 0. In principle, tension is not equal to 0, but because there is no other information here given, so let's assume that the minimum tension is equal to 0. Okay, so if the minimum tension is equal to 0, this equation becomes R over M times mg. M and M cancel out, so V minimum is equal to square root of R times the gravitational acceleration. So V minimum, what we get here is R is 1.10 meter and the gravitational acceleration is 9.80 meter per second square. Okay, and that is equal to 3.28 meter per second. Okay, so the minimum velocity for this problem will be 3.28 meter per second. Okay, so we are done the first part. Still we have to calculate the second part. Okay, all right, so if we are done with this first part, let me erase. Okay, all right, now let's see what we are asked to do. So second part is said that calculate the tension in the cord at the bottom of the arc. So that means we are now interested to find the tension when the ball is here at position 2, assuming the ball is moving at twice the speed of part A. Okay, so that means here we know the V, and the V is given as 2 times 3.28 meter per second. So now at this position, at position 2, the velocity is this. If the velocity is equal to this, then what is the tension? Okay, and again draw the free body diagram. So this time the tension will be in this direction and the gravity is always downward. Okay, so because the ball is here, the tension should be to the, I mean along the string, and the gravity is downward, and the acceleration, the centripetal acceleration is toward the center, so the acceleration direction will be this direction. Okay, now if we write the Newton's second law, this one will have T, positive T, negative gravitational acceleration, and then positive MAR. Okay, so we have to calculate T, mg, so this is positive sign, don't confuse with T. Okay, so plus M, and AR is V square over R. So we know that M is equal to 0.150 kilogram, and the gravitational acceleration is this one, plus again M is this kilogram, V is 2 times 3.28 meter per second square, and R is 1.10 meter. So if you plug these values in your calculator correctly, you should get something like this, 7.35 Newton. So the tension when the object, when the ball is at position 2, the tension is 7.35 Newton. All right, so let's move on. Okay, so the next few problem, actually next two problem is about the banked and unbanked curve. Okay, actually next three problems. Okay, so let's try to solve one by one. Two or three. All right, So this is the problem where we have a car whose mass is 100 kilogram. Okay, so this is so you see that the mass of the car is 100 kilogram. This is mass. The radius of flat, so this is unbanked. Okay, the radius of the unbanked curve is given 50 meter. Okay, and the velocity is given 15 meter per second. Now it asks us to, will the car follow the curve or will skid? Okay, so we have to determine whether the car with this information, the mass of the car is 1000 kilogram, the highway curve radius is 50 meter, the car is moving at 15 meter per second. So if so, whether the car is in the car will be in the curve or it will skid. Okay, given that the coefficient of friction for two different cases, one in a dry day and another in a icy pavement, so snowy day or okay, so you see that when it is dry, the coefficient of static friction is 0.6, and in when snowy or icy day it's like a 0.25. Okay, so how to solve it? Now let's say this is the curve. Okay, now to keep the car in this circular path, unbanked flat circular path, we need a force to the center of the circle. Okay, to the center of the circular path, and that we call the centripetal force. Right, now the centripetal force here, the minimum centripetal force we need here, that is equal to mv square over r. And let's first calculate that, what the minimum centripetal force we need, and then we check that whether the static friction we have, it is enough or not. Okay, so if we calculate this, it will give us okay, so if you plug these values in your calculator, it should give you this value. So the minimum centripetal force we need to keep this car, keep the car in this portion of the circular path is 4500 Newton. Okay, now if the static friction between the car tires and the ground is higher than or equal to this value, then the car will be in the track, otherwise it will skid away. Okay, now we have to check whether the static friction is 4500 Newton or less. Okay, so if it is equal or higher, then it will be in the track. If it is lower, then it will be it will skid away. Okay, so let's see. So for the first problem, when the mu s is 0.6, the static friction will be equal to mu s times the normal force, and the normal force, as you remember, is m times the gravitational acceleration. So if I plug the value of 60 for the coefficient of static friction, we get the value of static friction force is, that is good, right? This is higher than 4500 Newton. So the car stays in the track. Okay. Now how about for B? So for B, it will be 0.25 1000 kilogram and then 9.80 meter per second square. So what I get is very low number, 2450 Newton. Okay, so this means the car will skid away. Okay, so when the coefficient of static friction is higher, the car stays in the track. When the coefficient of static friction is 0.25, it will be skidding away. Okay, so this is about the unbanked highway car. Okay, and now the next problem is banked highway car. Okay, so let's see whether we can solve the banked one. Okay, and try to understand this. There are several homework questions on these. Okay, so this one is about the banked highway curve. Okay, all right. So what we are given. So we are given that the velocity is v, is a 50 kilometer per hour. So 50 kilometer per hour, it's better to convert it into meter per second. So v is given 50 kilometer per hour, and you now know how to convert it. So 50 times 10 to the power 3, and kilometer to meter is 10 to the power 3, and then hour to second is this 3600. So it is in meter per second, and I got something like this, 13.9 meter per second. So 50 kilometer per hour velocity means the velocity is 13.9 meter per second. Okay, so this is the one information. The radius is 50 meter. This is also given. So here you see the radius is 50 meter. Okay, now what it asks us to calculate, let's see. So determine a formula. So it asks us to determine a formula for the angle of which the road should be banked so that no friction is required. Okay, so you know that there is, although there is friction between the car tires and the ground always, but here we are neglecting the static friction. Okay, so even there is no static friction, we now know from the theory class that the car will for some condition the car will stay in the circular portion of the highway curve. Okay, all right, and now we have to I mean, it asks us to calculate what is the angle. Okay, determine the formula for angle theta. So we have to first determine the formula for angle theta, and then we have to plug the value, given value, into this formula and find what is the angle theta. Okay, so let's try to understand the free body diagram. Okay, and free body diagram I already discussed in the theory class, but let's do it again. Okay, all right, so when a car in a banked curve, okay, so it is something like this. The figure looks like this. Okay, it looks like it is in an inclined plane, right? So the only problem, I mean, only difference between the inclined plane problem and this problem is, in inclined plane problem we modify the coordinate system, right? Normally coordinate system is this. In inclined plane problem in the last chapter, you see that we modify the coordinate system this to this, right? But here remember that this is only exception when you do the inclined plane problems. Although it looks like the inclined plane problem, but we do not modify the coordinate system. So coordinate system is still our usual coordinate system, something like this. Okay, all right, so once we have that, the next thing is to draw the all the forces. Okay, so you know that the force we have here is the gravitational force. Okay, so this is the gravitational force mg, and then this is the normal force. Okay, so gravitational force and the normal force. If I draw in a inclined plane, so it will be something like this. So this is the normal force and this is the gravitational force. And because we neglect the static friction, we don't need to draw the static friction here. Okay, all right. Now if the angle, this angle is theta, okay, we can show that no, not this one. So we can show that no, I don't need this one. So we can show that okay, so we can show that this angle is also theta. Okay, so this angle is also theta. So here this is mg and this is the normal force and this is the theta. Okay, now what you see here is the x-axis is this one, y-axis is this one, right? So you see that mg is negative, is in the negative y-axis. That's good, so we don't need to break it. But the normal force is neither along x-axis nor along y-axis, so we have to break it. Okay, so if you break it, you get these two components. So one component is this one and another component is this one. Okay, and okay, so this component, because this is adjacent, it will be n cosine theta, and this component, let me draw it here. Okay, this is the same thing and it is n sine theta. Okay, so you see that n sine theta is in this direction to the center of the circle, right? So so because of this, I mean, because we already have something to supply the centripetal force, we do not need I mean, we do not basically need the static friction. I mean, although we cannot avoid it, there is already, I mean, in real life, there is already static friction. Okay, but even if you don't have a static friction, okay, it is not that a problem. So if it is in unbanked curve, then it is a serious problem. But when it is a banked curve, something like this, I mean, something like this current problem, it's not a big problem. Okay, so that's what I mean here. All right, so now we have to solve the, I mean, because we have to calculate, I mean, determine first the formula for theta. So we have to start from the Newton's second law. So Newton's second law for y direction is Fy equal to MAy. Okay, and you see in this free body diagram, there is no acceleration along the y direction, so the right hand side is equal to 0. Okay, then in the left hand side we have two forces. Okay, one is n cosine theta, that is in the positive y direction, and mg in the negative y direction. So if I solve this equation for n, it gives me mg over cosine theta. Okay, so that is the y equation, and let's try to solve x equation. So x equation is fx equal to max. Okay, so fx, we have what? We have minus n sine theta. Okay, so minus because the positive x is in this direction, but n sine theta is opposite of positive x, in the negative x direction. So that's why we have to use a negative sign. And in this direction, we have m, I mean, the centripetal acceleration direction is also this one, right? So the centripetal acceleration, because it's in this direction, we can write minus MAR. Okay, so this minus cancel out, so that's a good thing. Okay, now if I substitute the value of n, we get mg cosine theta sine theta equal to MAR means m v squared over r, right? So this m and this m cancel out. So in the left hand side we have g tan theta, sine theta over cosine theta is tan theta, and here we have v square over r. So what we get here is v square equal to rg tan theta. Okay, so this is the equation which relates the v square, relate v square and the radius and the gravitational acceleration and tan theta. So there is a homework problem where I asked to calculate the v. So if you want to calculate the v, you have to use this equation. Okay, so this is basically the equation we need, but here it asks us to find the formula for theta. So then we just need to play with this equation. Okay, this equation you need for homework, one of the homework problem where I think I asked you to calculate v for a band curve. So you probably need to use this equation, but for this problem you have to deal with tan theta. I mean, find the formula for tan theta. So tan theta is v square over r times the gravitational acceleration. So this is the formula. Now in the next problem, in number B, it asks you to calculate what is theta. Okay, what is the banked angle? So banked angle is theta equal to tan inverse v square over rg. So that is equal to tan inverse v square is 13.9 meter per second square. R is what? 50 meter, and the gravitational acceleration is 9.80 meter per second square. Okay, so what I get is theta is equal to 21.5 degrees. So if you plug this value in your calculator correctly, you should get the angle theta for this problem is equal to 21.5 degree. Okay, all right, so a lot of information I used here, so make sure you understand all. All right, so let's move on. Okay, so the number 7 is about non-uniform circular motion. Okay, so so as you know that when an object is in non-uniform circular motion, we have two types of acceleration. One is radial or centripetal acceleration, and another is tangent acceleration. Okay, so here it asks us to calculate both the tangential acceleration and the radial acceleration. So if you remember, the equation for the tangential acceleration is this delta v delta t, and delta v is the change in velocity, final velocity minus initial velocity. So here in this problem, it says that the object, the car, starts from rest. So the initial velocity is 0, and to a final velocity of this, so this is v, equal to 35 meter per second, and delta t is 11 seconds. So this is the delta t. So if I plug all these values here, we should get our tangential acceleration. And tangential acceleration will be 3.2 meter per second square. And then it asks us to calculate the radial acceleration. Radial acceleration is simple. Now, radial acceleration, it asks us to calculate the radial acceleration when the speed is 15 meter per second. So speed is now 15 meter per second. So this square, and the track radius is 500 meters. So 500 meters. So the radial acceleration is this. Okay. So these are the two accelerations. All right. So the next one. So how many revolutions per minute would a 22 meter diameter Ferris wheel need to make for the passenger to feel weightless at the topmost point? Okay, so let's say this is the Ferris wheel. Okay, and this is the topmost point. Okay, so the chair is here for the passenger. Okay, now it says that what should be the revolution per minute. So it asks us to calculate the frequency. Okay, so for what frequency the passenger here will feel weightless. Okay, now weightless means basically the apparent weightlessness. I mean, if a person has mass, the true, I mean, that person will always have some true weight, but apparently he or she can feel weightless. Okay, in the last chapter, when we solve the elevator problem, if you remember that apparent weight, okay, true weight means the gravitational force, right? This is the true weight, but the apparent weight means the normal force. So the person will feel weightless, okay, when the normal force is equal to 0. Okay, so weightless means when the normal force is equal to 0. When if n equal to 0, then the person will feel apparently weightless. Okay, all right. Now, when the person is here on the chair in a Ferris wheel, what are the forces? So there will be gravitational force, and because it is on the Ferris wheel, there will be a normal force. Okay, and because it is moving in a circular path, at this point the direction of the acceleration or the centripetal acceleration is this one. Okay, so this is basically the whole picture. Okay, now if I solve this equation, I mean solve this problem using Newton's second law, I should write something like this. Okay, because all the components of the forces or acceleration are along the y direction. We just basically need the Newton's second law y component. Okay, so what are the forces? Forces are N minus mg and then minus mar. Okay, so this minus sign because the gravity is downward, this minus sign because here you see ar is also downward. But for weightlessness, n equal to 0, so the equation is very simple now. Okay, and here m and m, minus and minus cancel out. You see that g is equal to ar. Okay, so that means the person at the top of the Ferris wheel, I mean at this position, will feel weightless when the centripetal acceleration is equal to the gravitational acceleration. Okay, so that's good, but it asks us to calculate the frequency, right? So to calculate frequency, let me substitute the expression for the AR, I mean for centripetal acceleration. That's our favorite form equation, and this gives us let me erase this side. Okay, so you know that v square, I mean from this equation we can write v square equal to rg, or v equal to square root of r times the gravitational acceleration. Okay, so this gives us the velocity, right? But it asks us to calculate the frequency. So to do that, let's substitute the equation for the velocity that relates the frequency, right? So v equal to 2 pi rf. So one of the equation we derived in theory class was 2 pi rf. Okay, so if I solve it for f, it gives us 1 over 2 pi r, and then r times the gravitational acceleration. Okay, so now 2 pi r means 11 meter. Okay, so see here, it's the diameter, right? Diameter is 22 meter, so the radius is 11 meter. The half of the diameter is, so if you have a circle, so this is the diameter, and from here to here is the radius. So radius is half of the diameter. So that's why r equal to 11 meter, and then again 11 meter, and 9.80 meter per second square. Okay, so if you plug these values in your calculator, it should give you 0.15 rev per second. So this is the frequency in second. Okay, but it asks us to calculate the frequency in minute. Okay, so because it asks us to calculate the revolution in minute, so we have to multiply it by 60, and that is in minute. Okay, so the number here will be 9 rev per minute. Okay, so for this problem, the number of revolutions will be 9 per minute. Okay, so I'm going to stop here, and in next lecture I'm going to solve a gravitational problem.